Hello everyone. In this quantitative analysis video, I'm going to be going over the Rio Tinto River and the pollution over the centuries and how it applies to quantitative values in class. So for background, the Rio Tinto River is a river in the southwest region of Spain that flows into the Sierra Morena Mountains and continues its path to the southwest where it empties into the Gulf of Cadiz at Huelva. And the mining of the Rio Tinto began with the Roman occupation of the mines. In the picture, there's one of the water wheels that was used for the mine. And the Romans were able to mine due to their advanced technology at the time, which during the Roman Empire was it was like a centerpiece of how they were able to advance so heavily. The water wheel was used to remove water from the mines from 80 meters below the surface. The Romans occupied large-scale mining operations for over 200 years. So the Romans ruled that area for centuries. The sulphide oxidation process was present on a massive scale following the operations by the Romans and onward through history until 2001. The mining operation ceased following the 200-year Roman occupation, and only small-scale companies attempted to reach economic prowess that the Romans could not through the mining. So centuries later, following the Roman rule, the Spanish occupied the Rio Tinto mines, and following the Anglo-Spanish War in the late 1700s, the Spanish government took over the full-scale mining operations of the Rio Tinto. A new demand for copper and sulfuric acid in the 19th century contributed to a new dependence on the mines in the 1800s. So by 1808, the oversight of the mine was catastrophic, and the Spanish government leased out the mining rights to a privatized company for a 20-year span during the mid-1800s. And this is where the Rio Tinto Company Limited was founded. They are still a company to this day, but this is their original logo. The Spanish government once again took over the mines in 1873, where it was sold to the infamous Rio Tinto Company Limited. The company controlled the mines from 1873 until 1980, and during this period, the sulfide contamination and dissolved heavy metals were deposited into the river at a dangerously high rate, which attributes to the very low pH and high hydrogen ion concentration in the river. And it started the pollution that we see to this day up until it was decommissioned in 2001. So in the present day, the Rio Tinto mines are no longer commissioned by the Spanish government due to the sheer damage done to the river. Due to the centuries of the Romans mining, Spanish government, the small companies taking over, just the excessive mining that caused all the pollution, that caused that redness from the iron ions in there. But it seems that the Rio Tinto has been having a growing ecosystem within its acidic environments that kind of attributed to scientists thinking that it could lead to discoveries of places such as like Europa, the moon, and its acidic environments in liquid, and that there may be extraterrestrial life that could be living in there. And now the quantitative chemical considerations for this. So Raman spectroscopy of mineral precipitation. Raman spectroscopy was used to study the evaporation and mineral transformation processes within the Rio Tinto environment. Micro-Raman techniques were used to analyze overall precipitate sequences, which revealed that the copiative group with the iron ions and the sulphate and the concubite, I'm not sure how to pronounce that group, precipitate largely encompass the first precipitates that were in the minerals within the lake or the riverbed. And the those main groups were followed by more iron sulfate groups of a lower hydration. And then there's a diagram that exemplifies the Raman spectroscopy process. And the mineralogical and elemental analysis, this is another way that the soil in the riverbed was studied. So the oxidation of sulfide ores and iron ores as a result of acid mine drainage have led to the dissolving of the heavy metals present in the Rio Tinto. At the microscopic level, it can be seen that these heavy metals, in specific iron 2, can be oxidized by microbes and ultimately result in the natural purification system that makes scientists wonder if this can exist on extraterrestrial planets and moons. And this can be analyzed through the mineralogical and elemental analysis from the sediment along the riverbed at different points in the river. Suspended particulate matter associated metals include arsenic, lead, and chromium. These were all able to be transported through the river system and into the estuary, where they can be taken into the coastal ocean surrounding the mouth of the river. So the metabolizing of the heavy metals by the microbes in the environment made it so that the heavy metals were suspended particulate matter. And so by suspending these particles, they can make it from the river into the estuary where it could be taken out into the ocean, kind of creating a purifying system within that river. And so the heavy metals were once dissolved in the acidic river and eventually embedded in the sediment and get trapped within the riverbed. So some of these metals that aren't suspended particulate matter get trapped in the riverbed, and we can analyze these samples and we can analyze how long they've been there and just how much there is of it in the riverbed. In the heavy metals that reach the estuary, the river deposit into the sediment just outside of the river in a distinct layer. You can see the heavier amount of these metals that deposited into the estuary compared to the riverbed. And the study exemplifies the impact of the microbial organisms that feed on these heavy metals and turn them into the suspended particulate matter, and ultimately lead to the self-stabilizing microbial environment in the Rio Tinto, which is, I think, fascinating. And now we move on to plasma mass spectroscopy. So here, the biological adaptation of plant species in the Rio Tinto is a unique and beneficial phenomenon that holds the key to pollution restoration. So not only the microbes in the Rio Tinto, but also the plant environment that's been growing around the Rio Tinto over these centuries has kind of made scientists wonder how they can exist in such an acidic environment. But through these studies of the plasma mass spectroscopy, we can see how these like flora have just been able to absorb some of the heavy metals and use it for their own good. So elemental analysis of plant tissue and the surrounding sediment was achieved through inductively coupled plasma mass spectroscopy. The aerial tissue of 97 species of flora in the Rio Tinto ecosystem were screened for heavy metals such as calcium, magnesium, sodium, manganese, iron, nickel, copper, zinc, arsenic, and lead, which include the heavy metals dissolved in the river. As calcium was a constant necessity for the aerial tissue within the flora in the area, it was determined that many of these species possessed excluders for the remaining heavy metals. So we were able to analyze this through the biological absorption coefficient, which compares the amount of soil concentration or plant soil element concentration as opposed to the plant's aerial tissue concentration. And that formula can be seen right next to it. From here, the overall uptake of the heavy metals present in the environment was analyzed. So the understanding now of this adaptation technique from plant life is essential to understanding how maybe in other acidic environments, plant life may be able to flourish, or even like I said before, many astrologists and others that are interested in growth on different planets and extraterrestrial life, this may be a key element to understanding how plant life here may be able to flourish there. And so it's said that the mining of the Rio Tinto began centuries ago, but it's very, I would say, cliche to just take word for it, like just by historical elements. So we're able to find out how long this mining has actually been going on through carbon dating of the sediment core samples. So the mining of the Rio Tinto sulfide deposits resulted in deposit of heavy metals such as copper and iron that dissolved into the river and increased the overall hydrogen ion concentration, the pH. It is well known that the large-scale mining near the low point of the estuary has contributed to pollution of the Rio Tinto in the 19th century to the 21st century. As I mentioned in the background, from the Roman age to the 1800s after the Anglo-Spanish War, up until the 1980s and up until the time it was decommissioned in 2001. But the truth is that the mining can be dated back to the Bronze Age, over 5,000 years ago. So we're talking thousands of years ago. This observation can be satisfied by analyzing the distribution of the pollutant species in the surface sediment of the river estuary. So this kind of makes us think how back in the Bronze Age they were able to accomplish these feats, like how the Romans had such advanced technologies, like how we see mining today. We just think, oh, okay, that's simple enough. But back then they didn't have the technology, and it kind of makes us think about what the feats they had to go through in order to achieve mining such a long time ago. And it's kind of cool to see the chemical contributions of this and how we can date it to this day back to 5,000 years ago. So the analyzed core samples were measured based on the ratios of zinc and copper concentrations in the sediment. The resulting samples were then carbon dated by the carbon-14 species in order to determine how long ago the samples were deposited into the river. So 5,000 years ago. And then extraterrestrial considerations. Now, this is what a lot of the data has kind of made scientists think about. Not only is there the microbes that are able to absorb these heavy metals and turn them into SPMs, but there's also the flora that's able to flourish in the highly acidic environment as we didn't think they were able to before. So the Rio Tinto mine pollution is easily observable due to its dark orange-red color. So we see that from this picture from the present day, it's very orange-brown, very, you can see dense with those heavy metals. And this photo displays, this photo displays Europa. So it's able to demonstrate how that photo from the background is just so vibrant in how microbial life within the river kind of gives hope to scientists of otherworldly places, like this photo that I have of Europa, Jupiter's moon. So we can see that there's also these heavy metals existing maybe in a liquid environment, and they may be in a highly acidic environment, just as the Rio Tinto. So analyzing this and analyzing all the samples through the plasma mass spectroscopy and the Raman mass spectroscopy, we're able to kind of wonder how, if these microbes can be applied in our Earth, if they can be applied in other extraterrestrial planets. And I think that's so unique, in that it's a very pinpoint example, and it's very, like, I think the Rio Tinto was the only place on Earth that we've been able to analyze this, and its implications are pretty unique. And so with microbes being able to consume these heavy metals and survive in a highly acidic environment in the Rio Tinto, it can be possible for life to exist in other acidic environments, such as the area underneath Europa's surface, which is theorized to be an acidic ocean. The way the bacteria and plant life are able to sustain themselves by expanding or expending unwanted materials or feeding on the iron and sulfide minerals within the river are a scientific marvel and can infer the possibility of extraterrestrial life elsewhere in the universe.